Hi there, welcome back. In this slice of physics, we're going to discuss the concept of power in an electric circuit. We're going to first start with understanding what the power supplied by a battery is and how this is related to a term called the battery's EMF. Then we'll look at the power that's dissipated by a resistor, such as a bulb, and we'll answer questions like which bulb glows the brightest, the one with the most current through it or the one with the least current through it? Or does it depend on which one has the largest or lowest resistance? Or perhaps it depends on which one has the biggest potential drop or smallest potential drop across the bulb. Well, it turns out that the answer is a little more complex than that, so we'll look at that as well. Let's take a simple circuit here where I have a battery that's lighting up a bulb. So this is the representation we have for a bulb. As you know, the positive end of the battery is the one with the stub, which is here, and the negative end is over here. And you know the job of the battery is to maintain a potential difference across its ends, so let's call that delta VB. And in this circuit, since current is defined as the flow of positive charges, the current would go in this direction. It'll leave the positive end of the battery and get to the negative end. In doing so, it'll pass through the bulb. So let's say, just to put a number to it, let's say delta VB in this case is 6 volts. So let's look at a positive charge that leaves the positive end of the battery and goes through the bulb and comes to the negative end. What happens to it after that? Well, that's where the battery's chemical reactions will push the positive charge from the lower potential to the higher potential. The charge doesn't want to go there, but the battery will use chemical energy to do that. So you can think of a battery as a charge escalator. So the positive charge that ends up on the left end at a lower potential, and let's say the potential at the lower end is 0 volts, it moves that positive charge up the escalator to where it gets to a potential of 6 volts. So as this charge goes from the negative end to the positive end, it's moving to a higher potential, and at the same time it's gaining potential energy. And we can write that as delta U. There is a potential energy that the charge gains from going to the negative to the positive end. And you know from our previous discussions that delta U simply equals Q times delta V. So the total potential energy gained is equal to the amount of charge the battery moves from the left end to the right end times the potential difference across the battery. While all this is good, it's actually more useful to talk about the rate of energy supplied by the battery. So you know that the time rate of energy is defined as power, and power equals the change in energy over the change in time. And since in this electric circuit we have a change in potential energy, this ends up just simply being delta U over delta T, and given our form there, that equals Q, and let me write it as delta Q to denote the amount of charge that was moved, times delta V over delta T. And I can write this as delta Q over delta T times delta V. And you know that delta Q over delta T is nothing but current, so this simply turns out to be I times delta V. So what this equation tells us is that the power of a battery equals the current supplied by the battery times the potential difference it maintains across its two ends. Now this potential difference of a battery has another name. It's called EMF, which is written as a script letter E that looks like that. So you could also see this written as I times epsilon, where epsilon is the EMF of the battery. In the olden days that used to be called electromotive force, and we've dropped that expansion as we have learned more about force and work and energy, but we have kept the symbol of epsilon, or the script E, to denote EMF of the battery. And for all cases in our course, we will assume that the EMF of our battery is exactly the same as potential difference across the battery. So whenever you see EMF in a question, think potential difference maintained across the battery. In practice, the potential difference across the battery can be just slightly less than its EMF, but we will ignore that small difference and assume this to be true always. And as a final point, you can relate all this to work done by the battery. In order to increase the potential energy of the charges going through the battery from lower to higher potential, the battery has to do work, and that's where it uses its chemical energy that's stored in it to do work on those charges, increasing their potential energy. Okay, that's all we got to say about the power of the battery. Now let's move on and look at this bulb. So when we look at this bulb, there is a potential difference across the ends of the bulb, and let's call that delta V subscript R. R is the general subscript for all resistors, and bulb is a type of resistor, so we will use that. Now I'm going to take a little bit of a tangent here and discuss something called ideal wires. So the potential difference across the battery is 6 volts, and as the charges move along this wire until the point that just before they enter the bulb, they would have lost a little bit of potential. Remember, there's electric field inside these conductors because there's potential difference across them, which is what facilitates the flow of charges. But here's where we're going to introduce the concept of ideal wires. In all our circuits, we will be working with ideal wires, and ideal wires have a zero resistance. Now, you know, in practical world that doesn't strictly make sense, but the point is, in this circuit, the resistance of this wire is much less than the resistance of the bulb itself, so we can ignore it and for all practical purposes take it to be 0. And if it is 0, and if I take a point over here and here, let's label these points as A and B, the potential drop across A to B is the current that's carried in that segment of the circuit times the resistance of that segment. And since the resistance of that segment is 0, this potential drop is 0 as well. Since I have ideal wires on both sides, before the bulb and after the bulb, and the potential drop across those ideal wires is 0, and I'm going to summarize that over here, delta V across ideal wire is 0. That's the important takeaway we got from this discussion. And so because that is true, in this case, delta VR will be the same as delta VB, so it'll also be 6 volts. And that potential difference facilitates current through the bulb. And as the current goes through the filament in the bulb, those do have a lot of resistance, and they heat up as a result and glow. So the bulb's light comes from the fact that the resistance in it causes the filament to heat up and it glows. And as the bulb glows, it's dissipating power. And our question is, how much power is dissipated by the bulb? So we are interested in power of the bulb. And once again, we can use this equation over here and say that the power of the bulb has to be the current that's going through the bulb times the potential drop across the bulb, which is delta VR. And the unit of this power is the standard unit of power, which is joules per second, because it's the rate of flow of energy, which is also called watts, as we have seen before. So that's written as capital W. So if you take the units of current and potential difference and simplify them, you will see that you'll end up with the same units as energy over time, which is joules over second, or watts. So here we have a nice equation for the power dissipated by a bulb, which is defined in terms of the current going through it and the potential drop across the bulb. Now we can derive other forms of this equation using Ohm's law. So we had Ohm's law, which told us that delta V was equal to I times R. And using that, I can, by substituting I times R for delta V over here, I get I times R, or I squared R. Or I could take this Ohm's law and rewrite it as I equals delta V divided by R. And so if I substitute that in here for I would have delta V times delta V. So that would be delta V squared divided by R. So all of these forms are valid for power dissipated by a bulb. So now let's address the question of which bulb glows the brightest. Brightness of the bulb, which is what we're interested in when we use bulbs, is basically a measure of how much energy it's putting out every second. So it's really a measure of the power. So brightness is a measure of the power dissipated by the bulb, or the power of the bulb. So for example, when you have a 75 watt bulb or a 100 watt bulb, you know that a 100 watt bulb glows brighter than the 75 watt bulb. So what they're telling you is the power of the bulb, or the power dissipated by the bulb. So whenever you're asked about brightness, think power. Now, going back to our questions, which bulb glows the brightest? The one with the most current through it, the one with the most resistance, or the one with the most potential difference across it? Well, you see you got different forms over here, and so the answer really is that it depends. And it's the interplay of these three factors as explained by these terms. So if you have two bulbs that have the same current going through them, the one with the bigger potential difference across it will have a higher power, so it'll glow brighter. On the other hand, if you have two bulbs where the potential difference across both are the same, then the one with the higher current would have the bigger power and so will glow brighter. Let's now move on to look at these two forms. This is a little bit confusing because if I look at the first form, it seems to suggest that as resistance goes up, power goes up, so brightness goes up. But the second form tells me that as resistance goes up, power goes down, and so brightness goes down. Once again, we got to remember that when we say those things, we're assuming that the rest of the factors don't change. So when we look at this form and say that as resistance goes up, the brightness goes up, that's only true if the current is not changing. So if I have two bulbs with the same current, then the one with the higher resistance will have the higher power. If I have two bulbs with the same potential difference across them, then the one with the higher resistance will actually have lower power and glow less bright. So it's the interplay of all of these factors that we always have to consider. And we'll take some examples coming up that'll work through these numbers to give you some more practice. In this slice of physics, we covered the concept of power in an electric circuit and touched upon a couple of related aspects. First, we learned about the EMF of a battery, which for all practical purposes for us is the same as the potential difference that's established by the battery by separating charges. Next, we learned that the power supplied by a battery equals the current supplied by the battery times its EMF, which is the same as the current times the potential difference across the battery. And then we learned about ideal wires. These are wires that have zero resistance and so have no potential drop across them no matter how long they are. So potentials in our circuits will change only when we go through a battery or a resistor of some kind, and the connecting wires are considered to be ideal wires and have no potential drop across them. And finally, we learned that the power dissipated by a resistor equals the current through the resistor times the potential difference across the resistor, very similar form as the battery. And then we rearranged this to get a couple of other forms using Ohm's law to discuss the relationship of the power to the interplay between current, potential difference, and resistance. So to answer the question of which bulb glows the brightest, we really have to look at how these things play together in using the right form of these equations. But we can always count on the fact that the one that glows the brightest is the one that has the maximum power dissipated. So brightness and power are one and the same. Thanks. I'll see you soon.